all, welcome back. Today we will be practicing for the Texas A&M Math Placement Exam. Math Placement Exam is a 90-minute online exam used to assess your math skill. This important tool will help your advisor determine which is the appropriate math course that you should enroll in. This exam will test your knowledge of trigonometry, logarithms, exponentials, and other algebraic topics. Calculators of any type will not be allowed while taking this test. So as we go through these problems, I won't be using a calculator either. No additional resources like textbooks, cheat sheets, formula charts, any of that kind of stuff is going to be allowed as well. If you'd like more information about this test, please click on the link below in the description, which will take you to the Texas A&M Math Placement Exam website. One last thing before we jump into the problems, I am going to be assuming a certain level of understanding as I go through these explanations. But for any of these problems, if you'd like for me to do a deeper dive and go through some of the more fundamental pieces that you'll need to know, please leave a comment below, and I'll make a separate video addressing those specific problems. Well, without further ado, let's start with number one. Number one says rationalize the denominator. And really what it's asking us to do is to rewrite this expression so that there's no square roots in the denominator. We have a rational number in the denominator rather than an irrational one. So to do that, what we need to do is multiply both the numerator and the denominator by the conjugate of the denominator. The conjugate of an expression in this form a plus b is going to be a minus b. So these are what we call conjugates. So in order to rationalize this denominator, what we need to do is multiply both the numerator and the denominator by 3 minus the square root of 2. So I'm going to multiply both the numerator and the denominator by this. I'm allowed to do this because really I'm just multiplying by 1. So it's kind of a fancy version of 1. And so I'm going to rewrite this as 14 times 3 minus the square root of 2 divided by 3 plus root 2 times 3 minus root 2. Now, I've got it written like this, and the next thing I want to do is just to multiply all this together. So in the numerator, I'm going to distribute the 14, and in the denominator, I'm going to distribute this whole first binomial to the second whole binomial. In other words, I'm going to multiply 3 by both of these terms, and I'm going to multiply root 2 by both of these terms. Sometimes that's known as FOIL. 3 times 14, again, no calculator here, so you might want to work this by hand, is going to be 42. And then 14 times negative root 2 is going to be negative 14 root 2. In the denominator, we've got 3 times 3, that's going to be 9. Then we have this instance of 3 times root 2 and 3 times negative root 2. So what ends up happening here is I've got plus 3 root 2, minus 3 root 2. And those will cancel each other out, right? Anytime you subtract something from itself, it equals 0. And that's kind of the whole point of multiplying by this conjugate, is to get rid of those square roots. So then we have minus square root of 2 times square root of 2, which is just 2. I'm going to leave this up here, although I'm going to simplify this in the next step. 3 root 2 minus 3 root 2 is just 0, so those go away. And then 9 minus 2 is 7. So as we can see here, we can reduce this a little further. We can divide both of these terms by 7. 42 divided by 7 is going to be 6, and 14 divided by 7 is going to be 2. So we get 6 minus 2 root 2. And there we go. That's the answer for number 1. Number 2 says, find the sum or difference as indicated and write your answer in simplified form. So here we're just subtracting 2 fractions. So what we need is a common denominator. And so, especially when you're working with expressions, the easiest way to find a common denominator is to simply multiply the 2 denominators together. So for this right-hand expression, I'm going to multiply it by x plus a over x plus a, which really just equals 1. But I'm doing this so that I can get the common denominator. And I'll multiply this other fraction by 2x over 2x. So let's go ahead and multiply that out and write this as just one big expression here. So we've got 2x times x plus 2a minus 3 all over 2x times x plus a minus x plus 6 times x plus a over 2x times x plus a. Jeez. So here's our new expression. We've got the common denominator, and now we can combine these. So we're going to just subtract the numerators and then leave the denominator just 2x times x plus a. Now I've got it as just one big fraction. The last thing to do here is to start multiplying all the expressions out and then simplify as much. The denominator doesn't look like there's really anything to simplify here. Even if I distribute the 2x, there's not going to be any like terms. So I'm actually just going to leave the denominator the way it is. But there's a lot going on with the numerator, so I think I am going to go ahead and multiply that out. Maybe I could cancel something out, maybe not, but I'm going to start this off. I'm going to distribute the 2x to both x, 2a, and negative 3. Then I'm going to multiply this x plus 6 times x plus a together. But I'm going to be careful because I have this minus sign. I want to subtract this whole expression, so just be careful there. Okay, I'm going to leave that minus there and put parentheses around the quadratic trinomial I end up getting with it. So here I've got 2x times x. It's going to be 2x squared. And then plus 4ax minus 6x, and minus everything that I'm going to get here. Okay, so x plus 6 times x plus a. I'm going to multiply x times x to get x squared, x times a to get ax, x times 6 to get 6x, and then finally 6 times a to get 6a. Now just to kind of kill off this last set of parentheses here, I do want to distribute this negative sign, and that way I'll just have one long expression. So I'm going to just negate all of these terms in this second part. Okay. Now I can combine my like terms in the numerator. I do have some like terms here. So I'll start with the x squareds. Okay, so I have 2x squared minus x squared, going to be 1x squared. Then I've got two of these ax terms, right? I've got 4ax minus 1ax is going to be 3ax. Then I've got negative 6x minus 6x is going to give me negative 12x. And then finally, I've got this minus 6a with no like terms to combine. And so that's it for number 2. There's nothing really more we could do here. I can't factor that out. Nothing's going to cancel out or anything like that. So I'm just going to leave my answer like that, and that takes care of number 2. Number 3 says factor and reduce to simplest form. And it looks like we've got a quadratic in both the numerator and the denominator, so we need to factor those separately. So I'm going to do exactly that. I'm going to factor both the numerator and the denominator. The numerator here is 6x squared plus 11xy minus 10y squared. And the denominator here is 3x squared plus 10xy minus 8y squared. There are a lot of different ways how you can factor this, but I'm going to go with grouping as my primary method. So to factor this by grouping, we need to split up this middle term such a way that we can actually execute the method. So we're going to split up this middle term into two numbers that multiply, give me 6 times negative 10, which is negative 60, and add up to 11. And so again, two terms that multiply to give you the product of a and c, add up to that middle term. And so that's going to be 15xy and negative 4x. If I multiply these 15 times negative 4, I get negative 60. And if I add 15 and then minus 4, I get 11. Now, once I split up that middle term, I'm going to factor out the GCF of both the first two terms and the last two terms. So out of the first two terms, I'm going to factor out a 3x. And so that'll leave me with 2x plus 5y. And then in the second group, I'm going to factor out a negative 2y, which leaves me with 2x plus 5y. Notice how in the two sets of parentheses, I'm getting the exact same expression. That means I'm doing this correctly. Okay, so my two factors here are going to be the 2x plus 5y that you see in the set of parentheses. And essentially what I'm going to do here is just like factor that binomial out like it's a greatest common factor. And then I'll be left with just the 3x minus 2y as my remaining factor here. So that's the numerator. Okay, so let's do the denominator. We're going to use the exact same method here. is factoring by grouping. And I know there's a lot of other methods out there. Okay, I even use other methods in my classes. So reverse box method, X method, there's a lot of different ways you could do it. But this is the way that I think it might be most efficient here. Here we're trying to find two numbers that multiply to give me negative 24 and add up to 10. That'll be 12 and negative 2. So I'm going to say plus 12xy minus 2xy, and then finally minus 8 squared. Just like with the numerator, I'm going to factor out the GCF out of each group. In this case, it would be 3x, leave me with x plus 4y, and negative 2y, which leaves me with, again, x plus 4y. Just like with the last one, since I've got the same thing in both of these sets of parentheses, that's my indication that everything's going well. So that is going to be one of my factors, x plus 4y, and the other one will be 3x minus 2y. So now I could rewrite this expression in factored form. I'm doing kind of the first half of this. It's going to be, here's my numerator, 2x plus 5y times 3x minus 2y, all over x plus 4y times 3x minus 2y. Notice how we've got the same factor in the numerator and the denominator, so we can simplify this out, assuming that doesn't equal 0. And we'll be left with our final answer here, which is 2x plus 5y over x plus 4y. That's it for number 3. Move on to number 4. Number 4 says simplify the following completely. We've got this nice big nasty expression here. It has a bunch of exponents, fractions, and all that. So we really just want to focus on our exponent rules here. Definitely look into what those exponent rules are. I'm not going to go over each and every one. I'm going to kind of assume that you know what they are, and I'll just kind of show you how this plays out. But first, I'm going to use the power to a power property, which states that I can multiply these powers. So we've got negative 4 times negative 3/4, which is going to be positive 3. So this will be x to the power of 3 cubed. And then we've got 2/5 times negative 3/4, which would be negative 3/10. That would be 6 over 20, which would reduce 3 over 10. Okay, so now we've got it set up like this, and now when you divide, we're going to subtract your exponent. So I'm going to just rewrite this as x to the power of 3 minus 2/3 times y to the power of negative 3/10 minus negative 5/6, which, just to simplify things, is going to be plus 5/6. And now you just have to be on point with your fraction arithmetic here. You don't get a calculator, so 3 minus 2/3 would be the same thing as 9/3. Over here, we've got a common denominator of 30. 9 minus 2 now is just going to be 7. This is going to be x to the 7/3 power. And then we've got y to the power of 25 minus 9 is going to be 16/30. And actually, that can be reduced. So instead of writing 16/30, I'm going to write 8/50. And there's your answer for number 4. Can't really take this any further. Number 5 says solve the following equation. 5 times x minus 7 minus 13 times x minus 7 minus 6. So what I would do here is just start by distributing 5 and distributing the negative 13. Here's another way you could solve this, and that is you could factor out x minus 7, but I think that's really just going to complicate things. Next, we're going to do the multiplication. We have 5 times x, which is 5x. 5 times negative 7, which is negative 35. Then we have minus 13, or negative 13 times x. And then negative 13 times negative 7, which is 91. We have this minus 6, which is just kind of hanging out there for now. Next, we want to combine like terms, and we've got two linear terms. The 5x minus 13x is going to be negative 8x. And then we've got negative 35 plus 91 minus 6. We're going to combine all three of those terms. That's going to become 50. My next step is going to be to subtract 50 from both sides. So we'll have negative 8x equals negative 50. And finally, divide both sides by negative 8. My final answer here is 50 divided by 8. Can't reduce that. Oh, no, I take that back. You can reduce that a little bit. We could divide both of those by 2. Get 25 over 4. and now it's fully reduced. So there's our solution for number 5. It's 25/4. Number 6 says find the point which satisfies both equations and what is the value of x plus y. So first we have to actually find what x and y are. We have a system of equations here, and although there are a few different ways how we can solve systems of equations, I think the way to go for this one is the method of elimination. So if you're not familiar with that method, I would highly suggest you Google it. There are other methods for solving systems like substitution or graphing, but I think elimination is going to be the easiest one to do here. And so with elimination, what you try to do is eliminate one of the two variables by combining the two equations. Now, if we do that the way it's written here, we're not really going to be able to eliminate anything. If we add the y terms, for instance, we'll end up with negative 1y, and same kind of thing with the x's, we'll end up with 1x. But what we can do is multiply both equations by a constant to force the coefficients of the same variable to be opposites and get them to cancel out. And so I'm going to multiply the first equation by 3 and the second equation by 2 so that I can force those x coefficients to be opposites. You know, this one will end up being negative 6 and this one will be 6, and then I can carry on with the elimination process. So this first equation becomes negative 6x plus 12y equals 36, and after I multiply the second equation by 2, I get 6x minus 10y equals negative 6, and hopefully you can see now why I did that. You can see that my x terms are plus or minus 6x. So when I go to combine these, they will be eliminated, hence the name elimination. So yeah, I want to add these two equations together. I'm going to combine them that way. This is going to go to 0. That's going to leave me with 2y equals 30. And if I divide both sides by 2, I'm going to get y equals 15. So now I have y, and I still need to get x. So I'm going to plug in this value for y into one of the other equations. And you can actually choose any equation you want. I'm going to go with this first one and substitute y, 15 in for y right here. So that's going to give me negative 2x plus 4 times 15, which is going to be 60, equals 12. So yeah, 4 times 15 is 60. So we'll replace that 4 times 15 with the 60. Then we'll subtract 60 from both sides and get negative 2x equals negative 48. And finally, we'll divide both sides by negative 2 and get x equals 24. So now I have x, and I already had y. And the question is, what's the value of x plus y? So x plus y is going to be 24 plus 15, which is going to give me my final answer, which is 39. All right, and that's number 6. Number 7 says 2 investments are made totaling $10,000. In 1 year, these investments yield $650 in simple interest. Part of the $10,000 is invested at 5.5% and the rest at 6.75%. How much more money is invested at 6.75%? So before we can determine how much more money is invested at 6.75%, we need to find how much money is invested at each percent. So what we need to do is set up 2 equations. First, let's define our variables. I'll let x be the amount invested at 5.5%, and I'll let y be the amount invested at 6.75%. Okay, that looks good. So now let's set up our equations. We've got first the fact that there's a total of $10,000 being invested. So the amount invested at 5.5% plus the amount invested at 6.75% is going to be equal to $10,000. It's going to be one of our equations. The other equation is going to be related to the percents here. So 5.5% is equivalent to 0.055, and we're going to multiply that by x, which is the amount invested at that rate, plus 0.0675 y, which is the amount invested at that rate. And that should totally equal $650. That's the amount of simple interest that we've earned. So now we've got a system of linear equations here that we need to solve. And I think the method that we should probably use here is substitution, where we take one equation, isolate a variable, and then plug it into the other equation. So I can rewrite this first equation, this x plus y equals 10,000, as x equals 10,000 minus y, essentially just subtracting the y from both sides. And that's going to give me an equation where x has been isolated. Now this method is called substitution, so we're going to substitute this expression, this 10,000 minus y, into x for the other equation. So 0.055 times 10,000 minus y plus 0.0675y equals 650. This is the equation that I'm going to solve that'll give me y, and then I can use y to find x. So to solve this, first I'm going to distribute this 0.055 both 10,000 and negative y. So multiplying this by 10,000 is just going to have me move the decimal over 4 places. So luckily that arithmetic works out pretty good. And it comes out to 550 minus 0.055y plus 0.0675y equals 650. Then we need to combine our like terms and just be real careful here. The arithmetic's surprisingly not as bad as I was expecting. But we need to subtract 0.055 from 0.0675. And that should come out to be 0.0125y equals 650. Then we'll subtract 550 from both sides. Here I'm going to divide by 0.0125 on both sides, which is going to give me 8,000. So $8,000 is invested at 6.75%, and since the total amount invested is 10,000, that tells me that the remaining 2,000 is going to be invested at 5.5%. So that's going to be our x. So to answer the question here, how much more money is invested at the 6.75%? And that's going to be a total of $6,000. $6,000 more is invested at 6.75%. And that's our answer for number 7. Number 8 says, given the linear equation 2ax plus 3by equals 7c, where a, b, and c are all greater than 0, if x decreases by 10 units, what is the corresponding change in y? So what we want to do is first solve for y so that we have a function with y isolated. We're starting with 2ax plus 3by equals 7c, and isolating y is going to require that we subtract the 2ax over to the other side, and then if we're trying to isolate y here, we want to divide everything by 3b. So y is going to equal 7c divided by 3b minus 2ax divided by 3b. So we've got this equation now rearranged so that we can see what y is going to happen, and the reason we're doing that is because we want to see what the corresponding change in y is when we change x. So this is what y would equal just straight out from this equation. But if x decreases by 10 units, we want to see how that'll affect y. So what we want to do here is replace x with x minus 10 because we are decreasing this value by 10 units. So now I'm going to just kind of rearrange this equation just slightly. First, I'm going to distribute this 2a. So I get 2ax over 3b minus 10 times 2a over 3b. So that'd be 20a. So yeah, we're distributing that negative 2a to both x and to negative 10. That's why this is plus. And so what we have here is we've got the original expression, okay, but plus 20a over 3b. So that's the amount that y will change by. So the way we want to answer this question is we could say we'll say if x decreases by 10 units, then y will increase by, this many units. Okay, so if x decreases by 10 units, then y will increase by 20a over 3b units. Number 9 says, line A passes through the points 2k plus 3, 4k minus 6, and negative 2, 16. Find the value of k if line A has a slope of 0. So to find the slope, we're just going to find the change in y over the change in x, delta y over delta x. And it says that the slope is 0, so it's going to make this equation like pretty simple here. So the change in y is going to be this 4k minus 6 minus 16. Okay, so just taking the first y value, subtracting the second y value, that's going to give me the difference between the y values. Similarly, I'm going to subtract 2k plus 3 minus negative 2, which is going to end up being plus 2. I'm finding the difference between the two x values. So that's the change in y over the change in x, and that should equal 0. Okay, it says the slope is 0. So then it says find the value of k. So I'm just going to simplify this equation. The denominator, I don't really care what this is, because I'm going to multiply both sides by whatever that denominator is, and 0 times whatever this ends up being is still going to be 0. So I'm just going to delete that denominator. Negative 6 minus 16 is going to be negative 22. And so now we've got a nice little linear equation here. We are going to first add 22 to both sides, and then divide both sides by 4. That's going to give us our answer, 22 over 4, which reduces to 11 halves, which is 5.5. So all those answers are good. They probably want the reduced answer, so either 11 halves or 5.5 is going to be our answer for number 9. Number 10 says Jay wants to make a box with no lid or top out of a 10 by 6 inch rectangular piece of cardboard. If Jay cuts squares with dimensions x by x out of each corner of the cardboard and then folds up the corners to make an open box, find a function that represents both the surface area and the volume of the box. So just to show you a little illustration of what's happening, let me go ahead and paste this image in here. So we've got this sheet of paper. We know it's 6 by 10. I'll go ahead and label that. And then we want to cut out the corners of the sheet of paper and fold the sides up so that it becomes a box with no lid like this. Now the side lengths of the little squares that we're cutting out are going to be x. So each of these little squares are going to be x by x. Now we do want to be careful here. The 10 by 6 is the length of the entire side here, so we want to make sure to take that into consideration when we solve this problem. So to find volume, we need to find the length times the width times the height. And so we want to think about what the length, width, and height of this box are. So this side length was originally 6, but it should be a little shorter here because we cut out these squares. And we cut out 2 squares from each side, so we're missing x and x from this 6. So that means that this dimension is going to be 6 minus 2x. The other side length, which was originally 10, same deal here where we're going to subtract the 2 x's. So this side length is going to be 10 minus 2x. And then as far as the height goes, that's going to be the height of the square. So that's just going to be x will be the height. So the volume here is going to be the length and the width and the height all multiplied together. So x times 6 minus 2x times 10 minus 2x. I'll start by just multiplying that x to the first binomial here. So I get 6x minus 2x squared. And then I need to multiply these together. So I need to multiply each term in the first binomial by each term in the second binomial. So we'll just do this one at a time. 6x times 10 is going to be 60x. Negative 2x times 6x is going to be negative 12x squared. And then we have negative 2x squared times 10 will be negative 20x squared. And then finally, negative 2x squared minus 2x squared. You multiply those, you get positive 4x cubed. So I want to put this in standard form, which means we're just going to rearrange the terms, put the cubic term first. Typically, you write these polynomials in descending order based on their degree. We can combine these two terms. Negative 12 minus 20 is going to be negative 32. And so now we've got a formula in terms of x for the volume of the box. So that's going to be our answer for part A. For part B, we need the surface area of the box. And this one's going to be a little bit easier, I think, because if you think about the original sheet of paper that we cut, the surface area of the box will be the whole surface area of this entire sheet minus these 4 squares. So one way to set this up would be 10 times 6, which is going to be the area of the overall sheet, minus
each of the 4 squares, so 4 times x squared. Now there's not much to simplify here. 6 times 10 is 60, and 4x squared is just that. There's nothing we can combine that with, so really the only thing that we can do here is to put this into standard form, negative 4x squared plus 60. And that's going to be our answer for part B.
Number 11 says solve for x in the inequality. 5x plus 2, all divided by x minus 10, is all greater than or equal to 3. So the first thing we want to do is subtract 3 on both sides of the equation. Now we need to find a common denominator so that we can combine these two fractions. So the common denominator is going to be x minus 10, and we'll multiply that second term by x minus 10 over x minus 10. Now we've got a common denominator so we can combine these, but right before we do, I'm going to go ahead and multiply the 3 and distribute it to both the x and the 10, giving me 3x minus 30. But now that I have the common denominator, I can combine these two fractions, and I'll have 5x plus 2 minus 3x minus 30. Just be careful that when you subtract the negative 30, you do change that to a plus 30. So we've got 5x plus 2 minus 3x plus 30 all over x minus 10. From here, I want to combine my like terms. So I've got 5x minus 3x. That's going to give me 2x. And then 2 plus 30 will be 32. So we've got 2x plus 32 over x minus 10 is greater than or equal to 0. Now to solve this inequality and any rational inequality, what you need to do is find out where on the number line this function is either above or below the x-axis. And the way I like to keep track of that is with a number line. And so I'm going to draw a number line here and mark the values that make either the numerator or the denominator 0. So the values that make the numerator 0, like if I put 2x plus 32 equal to 0, I'm going to get x equals negative 16. If I set the denominator equal to 0 and solve that equation, I'm going to get x equals 10. Now the reason why I'm setting each of these sides equal to 0 and then solving them is because the sign of the function cannot change unless it hits either an x-intercept or a vertical asymptote. So the sign can change anytime that x value makes either the numerator or the denominator 0. So I'm going to mark these two numbers on this number line. So I'm going to substitute in any number I want that's in each of these intervals and just check to see if it makes the function positive or negative. And I'm looking for where is it either 0 or positive. We know that at 10 it makes the function undefined, so it can't be 0 there, but it definitely could be 0 here. So we know that we're going to include negative 16 in our solution set, but we're not really sure about any of these other intervals yet. But what we need to do is just pick some number to plug into this function down here that's in this interval. So if I plug in like something like negative 20, that's going to give me a negative divided by a negative, which is positive. So I know in this interval I'm positive. I'm 0 at negative 16. And then in between negative 16 and 10, I can pick a number like 0, and that gives me a positive divided by a negative. So all the values in between negative 16 and 10 will be negative. And then finally, I pick a value greater than 10, let's say like 100, and that's going to give me a positive divided by a positive, which is also positive. So if I'm looking to find where the function is greater than or equal to 0, it's going to be on this interval at negative 16 or on this interval. And so the way I'm going to write that solution set is that x could be any number. So I'm going to use this as an element of the set symbol. Looks kind of like this. So it's an element of the set, negative infinity to 16, and I'm going to put a bracket on 16 because we want to include that one. And then union, looks like this U-looking symbol, from 10 to infinity. We do not want to include 10 because it doesn't actually equal 0 there. If you were to write this solution set using inequalities, you would say that x could be either less than or equal to negative 16, or x is greater than 10. You could write your solution set any one of these two ways. I typically see the set notation more than the inequality notation, but that's just me. But you could also use this one as well. And that's it for number 11. Number 12 says find the domain of the function below, and they give us this nice little function here. So the domain is going to be all real numbers except for those that will make the function undefined or not real. So the numbers that will make this function undefined will be those that make the denominator 0. So let's set the equation equal to 0 and then solve it.
And I think I'm going to make this not equal to 0 rather than equal 0 because we're really looking for the domain, which would be all the numbers except for these. So we'll solve this, but also we need to make sure that our function is outputting real numbers, and so we need to make sure what's underneath this square root is non-negative. So we'll make sure that x squared minus 3x minus 4 needs to either be positive or 0. So both of these have to be true, and so I'm going to join them with a logical and statement. So all the x values that satisfy both of these are going to be those that are in the domain. So let's start solving. On this left-hand one, I'm going to add 54 to both sides, and then I'm going to divide both sides by 6. 54 divided by 6 is 9, so x squared can't be 9. If x squared can't be 9, that means that x can't be either positive 3 or negative 3. Now I do want to be careful with my logical operators here. This is one complete statement. X cannot be 3 or negative 3. When I join this with the other statement, I need to find the x values that satisfy both. Now to solve this quadratic inequality, first I'm going to factor it, and this factors as x minus 4 times x plus 1. And we're looking for where this is greater than or equal to 0. And I think the easiest way to figure that out is to draw a number line and mark both 4 and negative 1 on the number line, because these would be the values that would actually make the function 0. And just do like a quick little super rough sketch of this parabola. Since I know these are going to be the x-intercepts at negative 1 and 4, and I know that this is going to be a parabola that opens up because the leading coefficient is positive, basically my parabola is going to do something like this. So if I'm looking for where this function is greater than or equal to 0, that's going to be to the left of negative 1, and including negative 1 because it does equal 0 there, and then also to the right of 4 and including 4. So my solution here is going to be that x can be less than or equal to negative 1, or x can be greater than or equal to 4. So we do have two statements here, both of which are compound inequalities. So all of this stuff has got to be true in order for the x values to be on the domain. It's a lot to take in, and so what I would advise is just to create a number line of both of these inequalities and then just look to see where we can find the overlap. So 3 and negative 3, those are just individual points. We're going to take those out of the domain. We're just going to draw an open circle on both of those. Now for the other one, it says x is less than or equal to negative 1, so I'll make sure to put negative 1 right here. X can be any number smaller than or equal to negative 1. So I'm going to put a closed dot on negative 1 and draw an arrow to the left, although I'm going to skip over this negative 3 because remember that x can't be negative 3 or else the denominator is going to be 0. And then finally, x can be any number that's equal to or greater than 4. So here's our final solution set. That's what it looks like graphed as a number line. But if we're going to write this as just one complete set, we'll say x could be any value or is an element of the set from negative infinity to negative 3. Then we have that little hole at negative 3, so we'll use the union symbol here. And then from negative 3 to negative 1, close that off. And then one more union symbol to grab that last set, which is going to be from 4 to infinity. Now, one little correction I need to make here is that we do want to include negative 1 and 4. So instead of these being parentheses here, I'm going to make them brackets. And there you go. Here would be the domain for this crazy looking function.
Number 13 says find the domain of the function below, and what we have is here is a piecewise function where the top piece is defined for when x is less than 0, or in other words on the left-hand side of the y-axis, and this piece is defined for where x is greater than or equal to 0, or in other words on the right-hand side of the y-axis. Now the only numbers that will cause this to be undefined and therefore can't be in the domain are going to be those that make the denominator 0. So for that first piece, we've got x squared minus 1, and that just can't be 0. Otherwise, we're going to have a divide by 0 error. So if we add 1 to both sides, we're going to get x squared cannot be 1. And if we take the square root of both sides, normally we would get plus or minus 1. But since this piece of the function is only defined for where x is less than 0 anyway, we're only going to keep this negative 1. We're going to ignore the 1 because that's not going to be on this piece. So on the second piece, if x is negative 2, that's going to cause a problem. That's going to cause a divide by 0 error. If I say x plus 2 can't be 0 and subtract
2 from both sides, I'm going to get that result. However, this piece is only defined for where x is greater than or equal to 0, so we can safely ignore this domain restriction. So the only domain restriction we have is that x can't be -1, and so if we write that as a solution set using set notation, we would say that x could be any number between -infinity and -1, and from -1 to infinity. Sometimes you'll see this notated with a little epsilon here to say x is an element of the set. This is going to be your answer for number 13. Number 14 says find the x-intercepts of the function, and they give us this rational function, if any exist. So normally you would find the x-intercepts by just simply setting the numerator equal to 0 and then solving that equation. But if you have a hole in the equation, you might get a number that actually isn't an x-intercept. So we need to check for those holes, and we can do that by factoring both the numerator and the denominator and checking to see if there's any x value that also makes the denominator 0. So the numerator 6x squared minus 7x minus 5 can be factored as 2x plus 1 times 3x minus 5, and the denominator can be factored as 2x plus 1 times 2x minus 7. Now that we have it in factored form, we can see that there is a factor that is in both the numerator and the denominator, and this is going to cause the hole in the graph. So we're just going to ignore this for now because all it's asking for are the x-intercepts, and that's only going to happen when 3x minus 5 equals 0. So I'm going to set 3x minus 5 equal to 0 and solve that. First I'll add 5 to both sides, and then I'll divide both sides by 3, and that gives us our x-intercept. So we have an x-intercept at 5/3, 0. And just to recap, the reason that we didn't set the other factor equal to 0 is because this actually does not cause an x-intercept. Since that factor also appears in the denominator, we know that x equals -1/2 is the location of a hole or a removable discontinuity of this function. So our answer here is just simply the one x-intercept at 5/3. Number 15 says find the vertical and horizontal asymptotes of this rational function, and this is the same rational function that we had in question 14. So the horizontal asymptotes, if the degrees of both the numerator and the denominator are the same, and they are in this case, notice they're both quadratic, then the horizontal asymptote will be y equals the ratio of the leading coefficients, in this case 6/4. We could reduce that to 3/2, and so that's going to be the equation of our horizontal asymptote. To find the vertical asymptote, we need to set the denominator equal to 0 and solve, but we do need to check for holes, and we already did that in problem 14. We wrote this function in factored form, and it looked like this. And so we can see once again that we are going to have a hole at x equals -1/2 rather than it being an x-intercept or a vertical asymptote. So the only vertical asymptote that we are going to get is going to be the one that makes the denominator 0, this factor right here. So we want to set 2x minus 7 equal to 0, add 7 to both sides, and then divide both sides by 2. So now we have the equation of the horizontal asymptote, which is y equals 3/2, and the equation of the vertical asymptote, which is x equals 7/2. Number 16 says we want to find the x and the y-intercepts for this cubic function. So first, let's go ahead and factor this function. We have a GCF of just x, so we can rewrite this as x times x squared minus 9. X squared minus 9 is a difference of two squares, so we can factor that a little bit further as x plus 3 times x minus 3. To find the x-intercepts, we do something slightly different, but very similar to what we do to find the y-intercepts. To find the x-intercepts, what we need to do is plug in 0 for y and solve for x. Okay, to find the y-intercepts, we want to plug in 0 for x and solve for y. Okay, that's because the x-intercepts lie on the x-axis, and every coordinate on the x-axis has a y-coordinate of 0. Similarly, the y-intercept is where your graph is crossing the y-axis, and all the points on that axis have an x value of 0. So let's first find the x-intercepts. To do that, we're going to plug in 0 for y and solve for x. So I'm going to go ahead and use my factored function here because it's going to be way easier to set this equal to 0 and solve it than up here. We would have to do this factoring anyway. So here we can see that our x-intercepts are going to be at 0 and then plus or minus 3. And then my y-intercepts will be what I get when I plug in 0 for x and solve for y. So I'm going to have y equals 0 cubed minus 9 times 0, which is just 0. Now we should have already known that was going to be the y-intercept because we knew that the graph was crossing the origin already from the x-intercepts. But yeah, my y-intercept is going to be at 0. The x-intercepts are going to be at 0, 0, 3, 0, and negative 3, 0. The y-intercept is going to be at 0, 0. All right, that's it for number 16. Number 17 says find the domain of the following functions. And what we've got here are 3 functions. So I've gone ahead and written their parent functions so that we can talk about what their domain restrictions are. The first one is a square root function, and its domain restriction is that the input has got to be either positive or 0. It can't be negative, or otherwise you're going to output non-real solutions. So x has got to be greater than or equal to 0. For a logarithmic function, same thing except it can't be 0, so it's just going to be strictly greater than 0. And for a rational function, the restriction is that the denominator cannot be 0. So we'll use these basic domain restrictions to solve these questions. We'll take them one at a time. For part A, we've got f of x equals the square root of negative x squared minus 4x plus 5. So all that stuff that's underneath the square root, the negative x squared minus 4x plus 5, has got to be positive or 0, so greater than or equal to 0. Now to solve a quadratic inequality, what we need to do is to go ahead and factor it, and this will be a lot easier to factor if I multiply everything by negative 1. So I'm going to go ahead and do that, and just don't forget to flip that inequality symbol. So now what I'm going to do is find the x-intercepts, and I'm going to do that by factoring. This factors as x plus 5 times x minus 1. And what I'm going to do is draw a little sketch of this parabola. I'm going to draw a little number line, and I'm going to label negative 5 and 1 because those are going to be the x-intercepts I would get. The reason why they're not the same signs as what you see in the factors is to get those x-intercepts, you'd have to set these equal to 0 and solve it. So for instance, if I have x plus 5 equals 0, I would subtract 5 from both sides and get negative 5. This parabola that I'm graphing has a positive leading coefficient, so I'm going to draw my parabola kind of going up. Now what I'm looking for here are the intervals for where the function's values are less than or equal to 0. And so we can see that these are going to be less than or equal to 0 down here. Okay, so in between negative 5 and 1. And this is an inclusive inequality, so we're going to say less than or equal to. So negative 5 is less than or equal to x is less than or equal to 1. We can also write this using set notation. We could say x is an element of the set, all the numbers between negative 5 and 1, inclusive. So I'll use brackets instead of parentheses to indicate the inclusivity. For part B, we've got a logarithmic function. The domain restriction for log functions is that x has got to be positive. So that means that 4t minus 3 must be positive. And so here we're just going to solve for t. This one's a little bit more straightforward than the quadratic one. We're just going to add 3 to both sides and then divide both sides by 4. So t is going to be greater than 3/4. We can also write this using set notation, just like we did the previous one. And then the way we'll write this to say that t is greater than 3/4 is we'll use parentheses, since it's exclusive, 3/4, comma, infinity. Part C is a rational function, and rational functions, since we can't divide by 0, have a restriction where the denominator cannot be 0. So what I'm going to say is that x cubed plus 3x squared minus x minus 3 cannot be 0. Now I'm going to factor this using a technique called factoring by grouping. You might want to look further into this if you've never heard of it before. I'm going to run through the steps, but I'm not going to give a bunch of examples or anything. But basically what you want to do is group the first 2 terms and the last 2 terms and factor out the GCF out of each group. So the first group, I can factor out an x squared. And in the second group, I can factor out a negative 1. So you can see now that the 2 binomials in the parentheses both have x plus 3. So essentially what we're going to do is factor this out kind of like it's a GCF, leaving us with x squared minus 1. We're going to set each one of these equal to 0 and then solve and then take those out of the domain. If x plus 3 can't be 0, that means x can't be negative 3. Similarly, if x squared minus 1 can't be 0, that means x can't be 1 or negative 1. So we've got 3 numbers that x cannot be. If x were any of these numbers, we'd have a divide by 0 error. And so this is probably the more efficient way of writing the solution set, but I'll also show it in set notation. It's going to have a few intervals because we're basically excluding these 3 numbers, but want to include everything else. So x is an element of the set from negative infinity to negative 3, but we're going to remove 3 out of the set, so we're going to use parentheses and then go from negative 3 to negative 1. I need to also take out a 1. All right, so there you go. This was really like 3 questions in one, but these are going to be all your answers for number 17. Number 18 wants us to simplify this expression, and we see we've got a bunch of terms here with exponents and square roots all over the place. I think the easiest way to approach this is to rewrite each term just kind of by itself and create a product rather than have all this division. And we could rewrite each term without the square roots simply by using rational exponents. So 2 is just 2. That doesn't really change much. And then we have times 1 over the square root of x to the 5th. Now, whenever you're dividing by something, that's the same as multiplying by the reciprocal, which is why it's okay to write 2 times 1 over, and then the square root of x to the 5th, which would be x to the power of 5. And then here's kind of the key thing here. The square root of anything is equal to that term raised to the 1/2 power. Okay, so I'm going to simplify this on the next step, but I want you to kind of see this step by step how I get there. Then we have times, and then we've got this product right here, which I do want to split up, but I'll do that on the next step. All I'm going to do here is rewrite that cube root as a rational exponent, as the raised to the power of 1/3. That's what the cube root actually means. So the next step I'm going to do is just to kind of clean up all of these powers. 2, I'm going to just leave that how it is. Whenever you have 1 over a power, that's equivalent to that same power, but negative. So one way we can rewrite this is to say, okay, well, we're raising a power to a power here. 5 times 1/2 is going to be 5/2. And then if we have 1 over that, that would be equivalent to saying x to the negative 5/2 power. So just rewriting this term right here as x to the negative 5/2. Then whenever you have a product that's being raised to an exponent, you can apply this exponent to each term individually, each factor. So we've got 4 to the 1/3 and x to the 1/3, and we're going to multiply all of these. Now the exponent rule for multiplying when you have the same base is you add the exponents. So you'll notice that we have the same base with these x's, but not the same base with the 4 and the 2. However, we can rewrite 4 as 2 squared. So what I'm going to do is just rearrange these terms a little bit, kind of regroup them, so you can see the powers of x and the powers of 2 all next to each other. So this 4, I'm actually going to rewrite as 2 squared. And when you raise a power to a power, you multiply those powers. So if I really have 2 squared to the 1/3, 2 times 1/3 is 2/3. So this 4 to the 1/3 is the same as 2 to the 2/3. The reason why I'm rewriting that as a power of 2 is so that I can combine it with this other 2, which is really to the power of 1. But typically, you don't write that. So now I've got just a product of powers with common bases. And then to combine these, all you need to do is just add those exponents. So 1 plus 2/3 would be 1 2/3, or 5/3, times x to the negative 5/2 times x to the 1/3. Well, we need to add these, and maybe I'll do this out to the side. Negative 5/2 plus 1/3. We need a common denominator there, which is going to be 6. So this would be negative, be 15 over 6 plus 2/6. So 2 minus 15 is going to be negative 13/6. Now we really do not like having negative exponents in our final answer, so I'm going to rewrite this one last time, and that is to put this on the denominator. So basically doing the reverse of what we did over here. So this is going to be 2 to the 5/3 divided by x to the 13/6.
And this is basically going to be your final answer. But if you really want, maybe this is a multiple choice question and all the answers are in terms of radicals, the way you would see this written is the cube root of 2/5 over the 6th root of x to the 13th. Now, I don't know how exactly it's going to look on your exam, but either of these two answers should suffice. They're both equivalent. It's just a matter of how you like them to look. Number 19 says if we begin with the graph of f of x equals x squared, which is the parent quadratic function, and shift f of x 4 units to the right, shrink f of x vertically by a factor of 1/2, and then shift f of x upwards 10 units, write the equation for the transformed graph. So this is just really a matter of understanding how transformations on functions work. So in general, if you've got an equation that's set up, you can transform the function by either multiplying or adding a number to the function itself or to the input. And so if you write your function in this form, the a value here will cause a vertical dilation. A b, which isn't going to come into play for this problem, causes a horizontal dilation. C causes a horizontal shift, and D causes a vertical shift. So if we're trying to write a transformed version of f of x, what we want to do is first shift it to the right 4 units. And so this C is going to be 4. We also want to shrink it vertically by a factor of 1/2. Well, that's a vertical dilation, and so we're going to change this to 1/2. There's no horizontal dilation here, and then we do have a vertical shift upwards 10 units, and so there we go. So this is what the function would look like in general, but if we wanted to write it in terms of x squared, we would just rewrite it like this. So if f of x is x squared, we'll just replace this with x squared like that. This would be the new equation. I'll just call it y equals. So here's your answer for number 19. Number 20 says solve the following equation for x, and we have this equation involving logarithms. So to combine these logarithms, we're going to use the product property, and what that means is we need to multiply the two arguments inside the logarithms together. So we have log of x plus 2 times x minus 1 equals 1. And then we'll go ahead and multiply these two binomials together, and that'll give me x squared plus 2x minus 1x minus 2, which would simplify to x squared plus 1x minus 2. And so now we have log of this expression equals 1, and now we can use the inverse property and invert this and write it as an exponential equation. So the base here, when you don't see a number written, is 10. So this would be 10 to the first power equals everything that's inside the parentheses. So x squared plus x minus 2 is going to equal 10 to the first power, which is just 10. So we'll subtract 10 on both sides, and that gives me x squared plus x minus 12 equals 0. And then we can solve this quadratic using factoring. This will factor as x plus 4 times x minus 3, and then we can set each of these factors equal to 0 and solve them independently, giving us x equals negative 4 and x equals 3. Now you got to be careful when you're solving logarithms. You want to test your solutions to make sure that neither one of them are extraneous. A logarithmic function has a domain restriction where anything inside the parentheses has to be positive. It can't be 0 and it can't be negative. So if I plug in 3 plus 2 is 5, no problem there. 3 minus 1 is 2, no problem there. But if I try to plug in negative 4, I'm going to get log of negative 2 or log of negative 5, and you cannot take the logarithm of a negative number. So this x equals negative 4 is what we call an extraneous solution. And x equals 3 will be the only actual solution here. So number 21 says factor the expression below completely, and then you just get this bonkers expression. What you need to do is look for, first, what is the GCF of this expression? In other words, what can we divide out from both major terms here? And what I'm really talking about, they're really not even terms, they're expressions, but I'm going to look at these two things in particular and say, okay, well, what can I divide out first from these coefficients? 3x squared and 64x squared. And the GCF there is just going to be x squared. 64 is not divisible by 3, so there's no coefficient that we can pull out.
and x squared is the most number of x's we can pull out of there. Now, if you look at the next part of each expression, it's 4x squared plus 1, and there's 8 of them in this first piece and 7 of them in the second piece, so we can take out or factor out a total of 7. 4x squared plus 1 to the 7th. Now, what's going to be left over is everything that I didn't actually factor out. So in the first group here, I didn't factor out the 3, and then there's one of these 4x squared plus 1s left over. And then in the second part, 64, we didn't factor that out, so we're going to leave that there. X to the 4th, we only pulled out an x squared, so that should leave us with an x squared left over. We did pull out all 7 of these, so there shouldn't be any remaining in this second piece. So now what I want to do is simplify what I have over here a little bit. So I'm going to leave that left part the same, x squared times 4x squared plus 1 to the 7th power times, all right, here we go. I'm going to first distribute the 3, and that's going to give me 12x squared plus 3, and then I'll just leave that 64x squared here temporarily. And then the last thing I'm going to do is combine my x squareds here. 12x squared plus 64x squared is going to be 76x squared. And I know this answer looks kind of funky, but this is just what it is. And that's it for this one. Number 22 says, how far from the base of an 18-foot pole must a person be standing if the angle of elevation from the ground to the pole is 41 degrees? So for these kind of problems, let's start by sketching out the scenario. So here we have a right triangle where the pole is 18 feet. The person is looking at the tip of the pole with an angle of elevation of 41 degrees, and we're trying to find the distance here. So this is going to use a little trigonometry, and we're going to use the tangent function, because tangent in a right triangle of an angle measure equals its opposite side divided by the adjacent side. So tangent of 41 degrees is equal to the opposite side, in this case 18 feet, divided by the adjacent side, in this case x. So if we're solving for x, we need to first multiply x on both sides, and then we're going to divide both sides by tangent of 41, and that is basically going to give us our answer here. So the distance is going to be 18 divided by tangent of 41, and you can put that in your calculator to get an estimated value. I'm getting about 20.7. You could also write this a little differently if you want to express the length in terms of cotangent rather than tangent. You could also write this as 18 times cotangent of 41 degrees, because cotangent is the reciprocal of tangent. So if you're trying to avoid fractions, you can write it like this. There's not like a huge advantage to doing it like that. I kind of like this 18 over 41 as the best answer. So that's it for number 22. Number 23 says find f of g, also denoted as f of g of x, where f of x is x over x plus 1 and g of x is 2 over x. So f composed with g, it just means that you have g being substituted into x for the f equation. So basically what we want to do here is we're going to write our f equation, and this is going to be f of x. But if we want f of g of x, then we need to substitute g of x wherever we see x. And so when we do that, we're going to get 2 over x instead of g of x, because that's what g of x equals, over 2 over x plus 1. And from here on out, it's just a matter of simplifying the expression. So first I'll find a common denominator in the overall big denominator here. And the common denominator is just going to be x. So I'm going to rewrite 1 as x over x. Now I can combine these two fractions down here by adding their numerators. This will be 2 plus x over x. Now when you're dividing fractions, that's really the same thing as multiplying by the reciprocal. So I'm going to rewrite this as 2 over x times x over x plus 2. Now notice here how we have a factor of x in both the numerator and the denominator, so those will reduce to 1. And so that leaves us with 2 over 2x plus 2, and that is going to be our final answer. This is going to be f composed with g, or in other words, f of g of x. Number 24 says perform the indicated operations and simplify, and you've got this really large expression here. So the first thing we want to do is let's change that division to multiplication. And we can do that, as you see here, by just finding the reciprocal of what you're dividing by. So now we can go ahead and multiply those two fractions together by multiplying their numerators and their denominators, just like that. So now we've got two fractions that are being subtracted, and so we need to find a common denominator to be able to subtract these. Now the easiest way to find a common denominator is to simply multiply each fraction by the other denominator, and that means we're going to be multiplying this first fraction by z plus 2 times y minus 4 divided by itself, and then we're also going to multiply the second fraction by x plus 1 over itself. That way we'll have the same denominator in both terms, just like this. Now we can start to simplify and clean this up. Firstly, I'm going to combine these two fractions now that I have a common denominator. So I'll just have this first expression, not even going to bother reading it, minus the second expression. And they should all be over since we have the common denominator, that product of x plus 1, z plus 2, and y minus 4. Our last step here, we're going to be simplifying this expression a little bit and writing it in standard form. I don't think it's really worth doing it to the denominator. We can leave that in factored form. But basically what I'm going to do here is multiply these two binomials together, then distribute the 8. I'm also going to distribute the negative wy to both x and 1. So our final answer here is 8zy minus 32z plus 16y minus 64 minus wxy plus wy all over, geez, what an answer here, am I right? X plus 1 times z plus 2 times y minus 4. And that's about it for number 24 here. Number 25 says solve the equation e to the 2x minus 2e to the x minus 3 equals 0 for x. To solve this one, we do want to factor this kind of like it's a quadratic. And to make this a little easier to digest, I'm going to make what's called a u substitution here. This is a common technique when you get to calculus. So I'm going to let u be e to the x. Essentially, I'm going to rewrite this expression but using u instead of e to the x, and I think it'll be easier for you to visualize how this is going to factor. Now the first kind of tricky thing is that e to the 2x is really the same thing as e to the x squared. Recall that whenever you raise a power to a power, you multiply the power. So if I have e to the x squared, that'd be the same thing as e to the 2x. And when I write it like this, this will just make that u substitution look a little bit more like what you might be familiar with studying quadratics. So here we go. I'm gonna let u be e to the x. This little u substitution trick is really just to make the factoring easier for you. So I'm gonna write this as u squared minus 2u minus 3 equals 0. Now I'm going to factor this, and you can see this is kind of a basic quadratic trinomial, and it would factor as u minus 3 times u plus 1. Now at this point, since I've already done the factoring, I'm safe to go back and replace that u back with e to the x, because from here on out, all I'm going to do is use that zero product property to set each one of these factors equal to 0, and I'm going to solve each one of these independently. For the first one, I'm going to add 3 to both sides, so that's going to give me e to the x equals 3. Now to solve an exponential equation like this, we need to invert it using logarithms. So that means I'm going to have log base e of 3 equals x, or x equals log base e, which is really just the natural log of 3. So that would be one of our solutions. And then the other solution that we could potentially get here would be the value that would make e to the x equal to -1, but that can never happen. -1 is outside the range of an exponential function, and you cannot input a negative number into a logarithm because of that. This actually gives you a no solution. So the only solution is going to be the natural log of 3. Number 26 says find the equation of the line passing through the point 5, 1 with a slope of 7. Use the equation you find to determine the value of y when x equals -4. So to answer this, we need to use the point slope form of a linear equation, which is right here. Y minus y1 equals m times x minus x1, where m is the slope and x1, y1 is some point on the line. So in this problem, the point that we're going to use is 5, 1. So I'm going to replace x1 with 5 and y1 with 1. And then the slope is 7. And so the question is asking to determine the value of y when x equals -4. So all we need to do is just substitute -4 into x. So I'm going to change this x to a -4 and now just solve for y. So -4 minus 5 is going to be -9. -9 times 7 is going to be -63. And then if I add 1 to both sides, I'm going to get my answer, which is negative 63 plus 1, or negative 62. Number 27 says if f of x is the square root of x plus 4, find and simplify f of 2 plus h minus f of 2 all over h. And this problem might seem kind of weird, but when you get to calculus, this problem will make a little bit more sense. What we need to do first is to replace x in this function with 2 plus h. So f of 2 plus h is going to be this function, but we're going to substitute 2 plus h in for x. And we'll do the same thing for f of 2, but instead of substituting 2 plus h in x, we're just going to substitute 2. So let's go ahead and simplify this just a little bit. 2 plus 4 is going to be 6. So we have the square root of 6 plus h minus the square root of 2 plus 4, which is 6. And now comes this next step, which is going to seem like it's coming out of nowhere. But again, when you get to calculus, what we're about to do is going to make a lot more sense. To simplify this, I really want to try to reduce an h here. Again, don't worry so much about why I'm doing that. That's going to come later. But the way to do that is to multiply both the numerator and the denominator by the conjugate of the numerator. So the conjugate of an expression in the form a plus b is a minus b. So the conjugate of this first root minus root 6 is that first root plus root 6. So what I'm actually going to do here is multiply both the numerator and the denominator by that expression. Okay, I'm going to change this minus to a plus. And what that's going to effectively do is allow me to reduce one of the h's out of here. So it'll let me cancel out a factor. So when I go ahead and multiply this out, what I need to do is multiply this by this, this by this, and then I'll also distribute the negative root 6 to both of these as well. So I'm going to end up getting the square root of 6 plus h times the square root of 6 plus h, which is just 6 plus h. I'm going to get the square root of 6 plus h times root 6, but then I'll get another one that's negative, so those two will cancel each other out. And then finally I'll have negative root 6 times positive root 6, which is going to equal negative 6. Now, the denominator is going to have h times all of this, so I'm not going to actually multiply that out, and you'll see why in a second. I'm just going to leave it in the denominator. So next up, I'm going to do 6 minus 6, which is 0. That's going to reduce these two. You can basically just erase those. And then now you can see how I'm going to reduce that h. This is what I was referring to earlier, where h over h is 1. So I can rewrite this in simplified form as just 1 over the square root of 6 plus h, the square root of 6, and that's going to be your answer. If you want a little bit more information about this, I know this is kind of an odd problem if you haven't taken calculus yet, but you might look into this strategy of multiplying by the conjugate. All right, that's it for number 27. Number 28 says simplify, and then you've got this big expression. So this is just a matter of understanding your exponent rules. Whenever you raise a power to a power, you multiply those powers. When I multiply 2 times 5, I'm going to get 10. When I multiply 4 times 5, I'm going to get 20. So I get x to the 10th, y to the 20th. And then I'll do the same thing with this next product. 3 times negative 3 is going to be negative 9. And then negative 3 times effectively 1 is just negative 3. Now I'm dividing by x, y, but I simplify this a little bit so I don't have a big fraction. I'm going to rewrite this as, instead of dividing by x to the first and y to the first, I'm going to multiply by the reciprocal, which is x to the negative first and y to the negative first. The last thing to do here is to combine all the like variables, and whenever you're multiplying two powers that have the same base, you add the exponents. So if I look at all my x's, and maybe it would be helpful if I just regroup them. Now you can see that I've got x to the 10th, x to the negative 9th, x to the negative 1st. You want to add all those up, and we get x to the 0th, which does end up being 1, so I'll take a note of that on the next step. Y to the 20th times y to the negative 3rd times y to the negative 1st would be y to the 16th. And since anything to the 0th power equals 1, this is just going to go away, and so our answer is y to the 16th. Number 29 says, simplify this expression. We've got two cube roots here and a bunch of stuff going on in between. This is going to be another exponent property problem. What you need to know is that whenever you take the cube root of something, that's equivalent to raising it to the 1/3 power. So I'm just going to rewrite this, and instead of using the cube root here, I'm just going to write to the 1/3 power, and then we can treat it like we did problem number 28. So first I'm going to multiply my powers. Anytime I raise a power to a power, I multiply those powers. So 1/3 times 3 is just 1, so we just left with a, and then we have b to the 1/3. Next we have 64 to the 1/3. The cube root of 64 is 4, and then a to the power of 4 times 1/3 is 4/3. And then b to the power of 2 times 1/3 is 2/3. The last thing to do here is to combine the like variables. I'm going to use the commutative property and move that 4 out to the front. And then here I've got a, which is a to the first, times a to the 4/3. 1 plus 4/3 would be the same as 3/3 plus 4/3. So this is going to be 7/3. And then 1/3 plus 2/3 is just 1. So this is just going to be times b. Now you may see this rewritten back as a root. So this a to the 7/3, one thing we can do here is we can rewrite this as like a to the 6/3 times a to the 1/3. 6/3 is the same as 2. So we have 4 times a squared times b times a to the 1/3. Now, you may see the answer written, like I said, with the cube root instead of with this rational exponent. So just to show you what that would look like, we would end up with 4 times a squared times b times the cube root of a. And that is going to be your final answer for number 29. Number 30 says perform the operations indicated and simplify, and then we just have this huge expression that we need to simplify. But when you really start looking at it, we have one fraction minus another fraction plus another fraction. So really this just comes down to understanding your fraction operation rules. Whenever you're adding or subtracting fractions, you need a common denominator. So if we want to try to pull all these together, we need to make sure all the denominators are the same. Now this is going to be easier, finding that common denominator, if we rewrite all three of these denominators in factored form. So I'll do that here. X squared minus x minus 2 is going to be x minus 2 times x plus 1. X squared plus x minus 6 is going to factor as x plus 3 times x minus 2. And x squared plus 4x plus 3 is going to factor as x plus 3 times x plus 1. And so when we're looking at our factors, what we want to do is multiply any factors from the other fractions that we don't already have, so that each fraction has the same set of factors in the denominator. So like this first one has an x minus 2, so does the second, but the third one doesn't. So I'm going to multiply this third one by that x minus 2. I can't just arbitrarily multiply the denominator by x minus 2 here. I do also have to multiply the numerator by that. So x minus 2 is accounted for in all three fractions. Now let's look at x plus 1. It's in the first one. It's not in the second one, so we'll multiply it here. And it is already in the third one. Then the last factor that we need to make sure is present everywhere is this x plus 3. And so we don't see that in the first one, so that first one I'm going to multiply by x plus 3 over x plus 3. Now we can see that we've got the same factors in each denominator, so we can start to combine the numerators, because the denominator will just stay the same. That, whatever your common denominator is, that's what it will remain. So I'm not even going to bother multiplying it out. Factored form is just fine here. The numerator will be the first numerator minus the second numerator plus the third numerator. And then the last thing to do here is to simplify, using the distributive property and combining like terms. So we'll do that in two separate steps, and we should have our final answer. First, I'll distribute the x squared. X squared times x is x cubed, and x squared times 3 is 3x squared. If I distribute the negative 4, I get negative 4x minus 4. And if I distribute this x on this last binomial, I get x squared minus 2x. My last step here is going to be to combine my like terms. I only have this one cubic term, so that's it. As far as quadratics, I have 3x squared plus 1x squared, so that'll be 4x squared when I combine those. And then I'm going to look at my two linear terms here, negative 4x minus 2x, and I get negative 6x. And then the negative 4 is just all by itself. So here is our answer for number 30. Number 31 says find all zeros, horizontal and vertical asymptotes for this rational function. So the first thing we want to do is to try to factor this and see if there's anything we can't simplify. So the numerator will factor as 3x plus 1 times x minus 5, and the denominator can factor as 4x plus 3 times x minus 5. Now notice how both the numerator and the denominator have x minus 5 as a factor. For right now, we can safely cancel that out, although technically we are changing the function a little bit. When x equals positive 5, the denominator becomes 0 and would make this undefined. So we're going to kind of ignore that for now, but it's not really going to affect how we find any of these characteristics of the function. What we're ignoring is the removable discontinuity that happens at x equals 5, and what that looks like on the graph is a little hole in the graph. But this question's not asking us for holes, so really we can just kind of focus on this simplified, although admittedly a little different function. The only difference that it has is that this one doesn't actually have the hole, or that removable discontinuity. From here, we're going to find the zeros by setting the numerator equal to 0 and then solve it. We'll find the vertical asymptotes by setting the denominator equal to 0, and then for the horizontal asymptote, we'll look at the coefficients of both the numerator and the denominator. So to find the zeros, we're going to set the numerator equal to 0, and then solve that. 3x plus 1 equals 0. So to do this, I'm going to subtract 1 from both sides, which gives me 3x equals negative 1. And then I'm going to divide both sides by 3, so I get x equals negative 1/3. And so that's going to be the 0. There's only one x-intercept here. To find the vertical asymptotes, I'll set the denominator equal to 0 and solve. I'm going to subtract 3 from both sides, so I get 4x equals negative 3. And then we'll divide both sides by 4 to get x equals negative 3/4. Finally, we want the horizontal asymptotes. To find the horizontal asymptote, we are going to look at the leading coefficients of both the numerator and the denominator. And you do this whenever the degrees of both the numerator and denominator are the same. So the leading coefficient of the numerator is 3 and the denominator is 4. So the horizontal asymptote of this particular function is y equals 3/4. All right, now that's all this is asking for. There is also a removable discontinuity at x equals 5, but it's not asking us for that. So at this point, we've finished answering this question. Number 32 says, if theta is in quadrant 2 and sine of theta equals 1/7, what is cosine of theta? So let's sketch a little diagram showing where the terminal side of angle theta is. So it's going to be somewhere in quadrant 2. We're not sure exactly where it is, but since sine is 1/7, we know that's the opposite side over the hypotenuse. So I'm going to make this opposite side here a little bit shorter than the hypotenuse. Angle theta is this angle right here. However, what we can do is use a reference angle, this angle right here, this positive angle measure, to help us answer this question. We'll construct a triangle using that angle measure. So yeah, here's a little right triangle, and it says that sine is 1/7, and since the ratio for sine is opposite over hypotenuse, I'm going to go ahead and label these as such. Cosine theta will be adjacent over hypotenuse, so we'll use a little Pythagorean theorem to find that adjacent side. However, we will label as negative because we're in quadrant 2, so our x values need to be negative. So we have 1 squared plus that adjacent side squared equals the hypotenuse squared. 1 squared is 1. 7 squared is 49. So that adjacent side is going to end up being the square root of 48. Now, since we're in quadrant 2, that does need to be negative because our x values are negative in quadrant 2. Now we're trying to find cosine of theta. So cosine of theta is going to be the adjacent side over the hypotenuse. The adjacent side is negative root 48, and the hypotenuse is 7, so this is going to be our answer. And we could simplify this a little bit since there is a perfect square factor of 48. Even though this is correct, we could write 48 as 16 times 3 and then take the square root of that 16. So you might, if this is a multiple choice question, see this written as negative 4 root 3 over 7. That would be equivalent, but also considered simplified. So each one of these is fine, but you might want to know how to actually simplify that square root. Number 33 says use properties of logarithms to expand the expression, and then we have the natural logarithm of root x times y to the 5th over z plus 1 to the 4th. And so the first property we're going to use is the quotient property to split this up into 2 logarithms. And basically that says that if you've got a quotient inside of a logarithm, you can split that up as a difference of the logarithm of the numerator and the logarithm of the denominator. Next thing I'm going to do is use the product property on this one to split these two factors up. So this will be the natural log of root x plus the natural log of y to the fifth. So this is called the product property. Next, I'm going to use the power property, which says that if you have log and then you've got a power inside the logarithm, you could bring that exponent down to be a coefficient. So here we've got 4 times the natural log of z plus 1. I can't really simplify this any further. We don't have like an addition property or something like that. So this is kind of fixed. The last thing to do is to use that power property on both the y to the fifth and the square root of x. Now the y to the fifth will be a little bit more obvious here. Right, the exponent is just 5, so I'm going to rewrite that using that as a coefficient, kind of like I did over here with the z plus 1 to the fourth. But the root x, I think, is not as clear-cut what to do there. What you need to do is realize that the square root of x is the same thing as x to the 1/2, and then we can use the power property to bring that 1/2 down to be a coefficient. And there's not really anything else you could do at this point. This is going to be your final answer for number 33. So 34 says, evaluate secant of 2 pi over 3 minus tangent of pi over 6. To answer this, you really need to be familiar with the unit circle. And so if you're not, I'll go ahead and pull it up here, but you really need to study this to be able to get this without having to look it up. So here's your unit circle. And what this does is it helps you to come up with all these different trigonometric values. So secant is the reciprocal of cosine. So if we can find cosine of 2 pi over 3, we just want to reciprocate it or flip the fraction, and we'll get secant of 2 pi over 3. So you can see 2 pi over 3 is over here in quadrant 2. Cosine is referring to the x value, so this is going to be negative 1/2. And so the reciprocal of that, which is secant, will be negative 2. Then we look at tangent, which is at pi over 6. Tangent is going to be the y-coordinate divided by the x-coordinate. 1/2 over root 3 over 2. Now when you divide 1/2 by root 3 over 2, both of these have 2 in the denominator. So effectively they're going to basically cancel each other out. But the way we'll write that is as 1 over root 3. So yeah, we want to rationalize the denominator for this fraction, which means we want to multiply this by root 3 over root 3, which will end up giving me root 3 over 3. And there's not much more you could do here. In fact, there's really nothing you could do to simplify this. I'm going to go ahead and leave it like that. The only thing I can really think of is to rewrite negative 2 in terms of thirds and combine those two fractions. So 2 would be 6 over 3. So this would be negative 6 minus root 3 all over 3. Either of these answers is probably okay, but if it is multiple choice, you want to be prepared to be able to combine those two fractions. Number 35 says if we begin with a rectangle with length 5 inches and width 4 inches, then increase the length by 8%, what is the change in area? So let's draw a diagram of that first rectangle. Now to find area of a rectangle, we just do the length times the width. So in this case, we have 4 times 5, which would be 20 square inches. Now let's draw a diagram for the new rectangle. So the rectangle's dimensions are pretty much the same. The width is exactly the same, but the length here should increase by 8%. So we're going to take the original length, 5, and then add 8% of that. So we can calculate that by multiplying 0.08 times 5. And so if we multiply that and then add back the original 5 inches, we should get 5.4 inches. And so if we want to compute the new area of this new rectangle, we'll do 5.4 times 4. And so if we do that, we get an area of 21.6 inches squared. Now, the question here is asking what's the change in area? And so we can see that we're adding 1.6 square inches. And so that's effectively going to be our answer, is the total change in area is 1.6 inches squared. Number 36 says evaluate f of 2 minus f of negative 3 given this piecewise function. So you have to make sure that when you're evaluating a piecewise function that you're substituting in your input into the correct expression. The first one here is going to be valid for when x is greater than 1, and since 2 is greater than 1, f of 2 is going to be 2 cubed plus 1, or 8 plus 1, which is 9. F of negative 3 is going to be using this second expression because x is less than or equal to 1, and negative 3 is smaller than 1. So we'll substitute in negative 3 into the second one. 2 times negative 3 squared minus 3 would be 2 times 9 is 18 minus 3 is 15. So if we're looking for f of 2 minus f of negative 3. That would be equivalent to asking what is 9 minus 15, and 9 minus 15 is going to be negative 6, which is our answer for number 36. Number 37 says simplify the expression cosine squared theta over 1 plus sine theta. So to simplify this, we need to be aware of our Pythagorean identities. And the one that we're going to actually use for this one is the fact that cosine squared theta is equal to 1 minus sine squared theta. So we're going to replace that cosine squared theta with 1 minus sine squared theta. So we have 1 minus sine squared theta over 1 plus sine theta. Now, kind of the trick to this one is seeing that 1 minus sine squared theta is a difference of two squares. And so if you're trying to factor a difference of two squares, the way to factor it is if you have something like a squared minus b squared. If it's in this form, you can factor it as a plus b times a minus b. And so our a here would be 1, our b here would just be sine theta. So we can factor that numerator as 1 plus sine theta times 1 minus sine theta. Now once you get it to this step, we can see that we've got a 1 plus sine theta as a factor on both the numerator and the denominator. So we will reduce that to 1, and that just leaves us with 1 minus sine theta, and that's going to be our answer for number 37. Number 38 says evaluate log base 4 of 1 over the cube root of 16. So we're going to use our logarithm properties to simplify this, and then hopefully it will be easier to evaluate since we don't get to use a calculator. This cube root of 16 is really the same thing as 16 raised to the 1/3 power, so I'm going to take advantage of that. But first, before I do that, I'm going to use my quotient property to split this up as log base 4 of 1 minus log base 4 of 16 to the 1/3. After this, we can start to evaluate. So log base 4 of 1 is just going to be 0. 4 to the 0th power is 1, and so we can evaluate that without a calculator. For the second logarithm, since we've got power here, we can use the power property to rewrite this as 1/3 times log base 4 of 16. So 0 is just 0. We can kind of ignore that at this point. And then so we've got negative 1/3 log base 4 of 16. Now, log base 4 of 16, you want to ask yourself 4 to what power is 16? And that's going to be 2. So we have negative 1/3 times 2, which is going to be negative 2/3. And that's it for number 38. Number 39 says simplify, and then we've got this expression here with a bunch of fractions. So this is really just going to test your fraction skills. Let's go ahead and rewrite this, but we need to find a common denominator for both the numerator and the denominator's expression. For the numerator, our common denominator will just be a, so we'll multiply b by a over a and get this fraction right here. Now we've got that common denominator. We can combine those, but I'll do that on the next step. Same kind of thing for the denominator's expression here. We need b cubed as our common denominator between these two fractions so that we can combine them. So I'm going to multiply this by b cubed over b cubed, and now I can start putting these fractions together. So for the numerator, my common denominator is a, so I can just combine these as 1 minus ab all over a. And do something similar here with the denominator. The common denominator is b cubed, so I can combine this as 1 plus ab cubed all over b cubed. Now I can divide these two fractions. When you divide two fractions, that's the same thing as multiplying by the reciprocal. So if I'm dividing by this big fraction here, I can rewrite that as times the reciprocal of that fraction. So I'm going to flip the numerator and the denominator on that second fraction. Now here, I'm almost done. All I need to do is just distribute the b cubed to both terms in this first fraction, and then I'll distribute the a to both terms in this second denominator. For the numerator, b cubed times 1 is b cubed, and then b cubed times ab is going to be ab to the 4th. And then now I'm going to distribute the a to both of these terms. So essentially I'm going to do a times this thing in parentheses. A times 1 is just a, and then a times ab cubed is a squared b cubed. And so here is your final answer for number 39. I don't think there's really anything else we can do here. Number 40 says a bacteria culture contains 1,200 bacteria and doubles every day. How many hours will it take the culture to reach 1,000 bacteria? So what we want to do is write an equation for exponential growth. Now, just in general, our exponential function is going to be y equals a times b to the x, where a is the initial population, b is our constant multiplier, and then x is going to be, in this case, time. So our initial value is going to be 1200. Our multiplier is 2 because it's doubling every day. And we want to know how many days, that's going to be our x, will it take for the culture to reach 10,000 bacteria, which is going to be our final amount. So here we've got an exponential growth equation that we need to solve for x, which will give us the number of days that it will take for the culture to reach 10,000 bacteria, and then we'll convert that to hours. All right, so the first step is going to be to divide both sides by 1200. And remember, we do not get a calculator here. Let me reduce this fraction here just to make everything a little bit easier. When you're trying to reduce these big numbers, you can always just cross out pairs of zeros here, essentially just dividing both sides by 100. We do get 100 over 12, which both of those numbers are even, so we can, at the very least, divide both of these by 2. If we do that, we get 50 over 6, and we can see that we can reduce that even further to 25 over 3. So now comes the part where we have to know how to isolate a variable that's in an exponent like this. And so to do that, we need to invert this equation using logarithms. The base will be 2. The input to our logarithm will be 25 over 3. And then our output will be this x, since we're inverting this exponential equation. So x is going to equal log base 2 of 25 over 3, and that equals the number of days for the culture to reach 10,000 bacteria. Now, if you're doing this problem too quickly, you might just think you're done here, but it actually asks for hours. So there is a unit switch. So this is going to give us the number of days, but if we want to know how many hours it'll take, we need to multiply this by 24, since there are 24 hours in a day. So it'll take 24 times log base 2 of 25 thirds hours for the culture to reach 10,000 bacteria. And that's about it. This is our last problem on the math placement exam. I really hope you found this video helpful. Please reach out if you have any questions, or if there's any problems you want me to do a deeper dive on, let me know in the comments below, and I will make sure to do an extra little video that goes into a little bit more detail about really any of these problems that you're curious about. So other than that, thanks for watching, and y'all have a great day.